Good afternoon, everyone. Again, this is our last but one lecture 40 in high-dimensional probability and its applications to data science. As promised, this last week is spent on a couple of very useful tools in high-dimensional probability that have wide applications. Probably the most useful that I wanted to present to you in this last week. Specifically, last class we proved Dudley's inequality, which allows us to put a uniform bound on basically any stochastic process. So let's consider any stochastic process at all. Let's say a mean zero. Mean zero means that all random variables involved in this process have mean zero. We can always do that by subtracting the mean. Mean zero stochastic process. On arbitrary set. Now, as we discussed, we can automatically turn that set into a metric space. So I'll assume that this is a metric space already. TD. Metric simply means that there is a notion of a distance. Excuse me. There is a notion of a distance between points in T. And that distance is denoted by D. In this form of Dudley inequality, we assume that the process is sub-Gaussian. Generally, you don't need to assume that. You'll have a different bound then. So the sub-Gaussian norm, let's say, is smaller than something, some constant k, maybe like 10 times the distance. So it's k, the sub-Gaussian norm of the increments is at most proportional to the distance between the points. Then we have the following bound. So this is what, okay, don't try this yet. This is what we would like to bound. We first take the supremum over xt. So we take the maximum possible value that the process can take, and then we average it. It is important that expectation is out. So it's important that the supremum is inside the expectation as opposed to outside. By keeping it inside, we want to bound the whole process uniformly, which means that we're looking at the maximum point, the maximum value the process can take, the maximum value of the stock, let's say, that over the period of time. We actually achieved a little bit more, and we'll need it today. We achieved this like this: xt minus xt0. Then for any t0 in T, for any reference point. And then, I'm sorry, then we don't even need mean zero in this version. Just a stochastic process. We bound this by some absolute constant times k times this funny looking integral. Integral of the metric entropy. So NTD epsilon, this is the covering numbers. Covering numbers. This is simply the smallest number of balls, of epsilon balls, needed to cover T. Log of that number, the logarithm, is called metric entropy. When we integrate that information, integrate the square root of that, we get some quantity that is a geometric quantity. So the right-hand side of this bound of Dudley inequality captures the geometry of T only. It doesn't have any randomness in it. It's just a geometric property. You can compute this for any metric T, right? It's not related to any randomness or probability. The left-hand side is purely probabilistic. There is no geometry in it. And this is how Dudley inequality is is powerful and also beautiful is that it establishes this link between probability and geometry. It's also important to note that the right-hand side is multi-scale, which means that it's not just enough to look at how many balls of fixed radius cover T. We do this for all possible radii, for all possible sizes of the balls. So it really kept the right-hand side, therefore captures some kind of multi-scale geometry of T. Okay, that's Dudley inequality. The plan for today is we'll show how to apply this, and especially how to apply the proof of Dudley inequality, which is more important. The proof is by chaining. Any questions before we do that?
Yeah, I have a question. So why mean zero is not necessary in here?
Yeah, if I'll give a intuitive answer and then the formal answer. So the intuitive answer is that it's not important because we subtract xt minus xt0. And so it kind of cancels. Let's say if all xt's have the same mean, let's say mean 10, then by subtracting it will cancel. But the formal answer is this. If you look at the proof of how we actually, where did we actually use mean zero? We use it exactly once when we got rid of xt0. So first we proved this bound. Then we used mean zero assumption to get rid of xt0. But in this version, I don't get rid of xt0, and therefore I don't have to assume mean zero. So that's why.
I see. Thanks.
Sure. Good. Any other questions before? Cool. Okay. So today we make an application of this of Dudley inequality to the problem where we started this course, the very first lecture, the Monte Carlo integration. Where we, let's say we want, in the very simplest case, we just want to integrate some function f of x on the interval from 0 to t, just like this. So we want to find this area, and to find this area right there, 0 to 1. And the way we do this is we turn this into a probability question by interpreting the expected value as by interpreting the integral as expectation. So it's expected value of f of x, where x is uniformly distributed random variable on 0, 1. Good. Okay, and then we use the law of large numbers to compute this expectation approximately from a sample. So instead of computing the expectation, we just sample random variables, uniform random variables. So make the sample xi right here, and average these values. So 1 over n f of xi, where xi are also independent, identically distributed uniform random variables. So this holds with high probability. That's what law of large numbers is saying, that the expected value is approximated by the sample mean. Good. So that's a numerical randomized algorithm for integration. Just take the sample, take the average, take the arithmetic mean of the sample, you're done. Now, question. Can we use one sample, the same sample, to integrate all functions, any functions you like? To integrate any function. Think about this like this. Can we just take the sample once and forever, fix it, let's say put it in the hardware of the computer, and then the computer can integrate any function from the same sample? Or do you think? No, of course. Yeah, why not, Daniel?
Because we can construct such a function which is, for example, which is not concentrated on these points from the data.
Exactly. So if you have a sample like this, for example, whatever sample we take, maybe these 4 points, the adversary can always pick a function that maybe just concentrated on that sample, and just like this, just makes value 1 on the sample and 0 elsewhere. And the sample mean will be large, but the true mean will be small, and so yeah. So not possible. Okay. And today we're proving that you can do this. Actually, it is possible to do if the function does not fluctuate. This is not like this crazy function that goes up and down. So it's yes for Lipschitz functions. And Lipschitz means that f of a minus f of b is less than absolute value of a minus b. Sometimes some constant, maybe L times a minus b for any a and b. So we'll call this function an L Lipschitz function, let's say. If you are not very familiar with this, any function that is differentiable is automatically Lipschitz. And if its derivative is uniformly bounded by L, then this function is L Lipschitz. Just divide both sides by a minus b and let a be close to b. You'll see the derivative coming up of this, right? And this, so Lipschitz, the notion of Lipschitz function is a little bit more general than the derivative. For example, the absolute value function is Lipschitz, just like this, but it's not differentiable at 0 because it has this point. So it's allowed to have some non-differentiability points, but generally it's like a differentiable function. Good. So we'll prove this theorem that says that you can integrate any Lipschitz function from one sample. So we consider the class of all Lipschitz functions, all functions that are 0 to 1, L Lipschitz, and we don't need uniform distribution. In fact, any random variable, any distribution is okay. And xi's be IID, independent and identically distributed copies of x. And again, copies means that we're taking them from the same distribution. It's just a sample from this distribution. Then, if you look at the sample average and compare it to the true mean, which will be the integral in the bound is like this. So this one, the rate of decay, the 1 over root n rate of decay, like this. This is optimal. This is the same as you get for one function. If I just put one function and compute the variance, do the variance argument as we did many times. You'll see that the rate of decay has to be 1 over root n. You can't beat that. What's beautiful is that we're able to prove this uniformly for all functions, and the rate doesn't even change. We had theorems like this before, similar to that, in that spirit, uniform limit theorems, and we deduced them from VC theory. This one we can't deduce from VC theory. And that's because the VC, Vapnik-Chervonenkis theory, only works for Boolean functions. And this is not a Boolean function. There are extensions of VC theory for general functions, but we're not concerned with those. So VC theory doesn't work. We have to do something different. We'll use Dudley inequality instead. And before we do this, any questions? Good. Okay, let's do it. Let's prove it. So for the proof without loss of generality, or maybe just for simplicity, let's assume that L is 1. L is just this constant for Lipschitz function that defines Lipschitz. Just assume it's 1, just to make our life easier. We can also assume without loss of generality that let's say f of 0 equals 0. Again, why? Because we're concerned about this difference. So if f of 0 is not 0, we just subtract f of 0. We can like vertically displace all the functions, and that will not affect the left-hand side. Right? If I subtract the same value for functions, it doesn't affect the left-hand side because it's subtracted, kind of cancels here. So let's do that. So our class of function will be this from 0 to 1 to r. F of 0 is 0, and f is 1 Lipschitz. Cool. Okay, we're going to apply Dudley inequality. Dudley's inequality has, where is it? Sorry, right here. Where's Dudley inequality? Here we go. So Dudley inequality is in terms of this metric entropy. So we'll have to compute that. We'll have to compute the covering numbers of f. And we will compute it for the strongest norm possible on functions, which is a sup norm. The supremum, the maximum overall, uniformly everywhere. So we'll prove that the covering number of this class in the sup norm, and this just a reminder that the sup norm or L infinity norm measures the worst possible, the largest possible value of f, absolute value. So that's kind of, this is the strongest norm you can think of for functions. And even then we can prove it. So this is, we'll prove that it is less than c over epsilon in the non-trivial range. And then it is just 1. The proof is simple. It's very geometric. Let's do this. First of all, in the trivial range, if epsilon is large, if epsilon is greater than 1, let's see why the problem becomes trivial. Because f of x, you can think of it as f of x minus f of 0, because f of 0 was assumed to be 0. We assumed that. But f is 1 Lipschitz. So 1 Lipschitz assumption gives this. And x is less than 1. So my point is that all functions in this class are already bounded by 1. So if you just take a 0 function, it's already approximates the 0 function, just one function approximates any function in this class with error 1. And so the covering numbers are trivial, are just the epsilon net is just one function, 0. Yeah, agreed? In the trivial range. Okay, in the non-trivial range, things are a little bit more interesting. Epsilon is less than 1. Okay, so here's the geometry. Here's how what's our job here? Our job is to find an epsilon net, to find a finite subset of functions that approximate nicely any Lipschitz function. Here's how we do this. We put a grid on, let's say, okay, let me try to draw a nicer picture. So let's say this is 0, this is 1, and I put a grid. We know already that all functions, the graphs of all functions, are within this rectangle. The domain is between 0 and 1, and the range we already computed is between -1 and 1. So all the graph is there. So I will approximate the graph. How? Well, in a very simple way. I'll just put this grid like that. Make it larger for you guys so you can see it better. Put the grid. Okay, now and the grid will be of size, let's say epsilon. I think epsilon will work. Epsilon here, epsilon here. Perfect. Now look at any function, any Lipschitz function, for example, this one. This is our f from the class. How do we approximate it? Let me just say it in words, or maybe just look at the picture. So proof by picture. Here's how we approximate it. The function goes up. So I will make it go up but now I'm fixing it to the grid. So I approximate the function on the grid. It goes up, then it goes up here, then it goes down. My picture is not perfect, but I hope you get the point. So I approximate the function to the nearest point on the grid, and then I'm just interpolating linearly, just like that. So this will be my function g, and the set of all such functions. Let's call this f epsilon. So what we do is we approximate any function f by some function g that takes value on the grid. Now, how many functions g can we make this way? Because f is one Lipschitz, it cannot really jump very high or down, up and down. At every step, f can either stay put or go up 1 by 1 or go down by 1. This is the all range, right? Remember, f is one Lipschitz means that over the interval, over one interval of epsilon, it can either go up by epsilon or down by epsilon or do something in the middle, but not more than that. So which means that at any step, at every step, g can be constant, so just be flat, or go up and down, or down by 1. By epsilon. What I mean is g can either go like this, either like this, or like this, or like this. These are exactly the three possibilities that this g can make. Agreed? Okay, then we know how to count them. So the number of such functions, G is at most, well, at each step, there are three possibilities, up, down, or zero. So 3 times 3 times 3 times 3. How many steps we have? We have 1 over epsilon steps. Because the interval is unit, it's 1. Each step is epsilon, so we have 1 over epsilon steps. So we get 3 to the power 1 over epsilon. Done. That's it. So we proved, actually we proved it better. We proved 3 to the power 1 over epsilon. We proved this lemma. Good, agreed. Okay, we approximated all Lipschitz functions now. We now have the bound on the covering numbers, and we can apply Dudley inequality. So proof of theorem. Proof of the theorem, let's do it. Expected value. This is what we want to bound. This. Okay, we're applying Dudley, so we call this thing, we call this X sub F. So we will apply Dudley for the stochastic process X sub F, which is indexed by Lipschitz functions. This is an interesting process, right? Usually stochastic processes are indexed by time, but we've seen such things before, but when they're indexed not by time, but in this case by functions class. Yeah, who cares? It works, right? So this XF, right? So this is let's see. I want to bring this to the form of Dudley inequality. Let's see. We go up a little bit. There's my Dudley. Here we go. This is Dudley. Let's look at this one more time before we apply it. So we needed to bring it to this form. Okay. So we will do it this way. We know that zero function, for zero function is Lipschitz, definitely, it's in our class, and x0 is trivially 0, like you just replace f with 0, you get a 0. So I can write it in this form then, just artificially subtract 0 and apply Dudley inequality. Good. So for Dudley inequality, we need to check that xf minus xg, this increments, we need to bound this, we need to prove that this process is sub-Gaussian. So let's do it. So what's xf minus xg? That's 1 over n sum of something. So if zi is f minus gxi minus expected value of f minus g xi. Yep, I didn't do anything. I just subtracted xf minus xg, and that's it. But these are IID, independent and identically distributed, mean zero, random variables. Mean zero because we just subtracted the mean literally here. And they are bounded in absolute value by 1. Actually, not 1. They're bounded by the sup norm of f minus g. Agreed? Just trivially bounded by the sup norm. Perfect. So there are IID mean zero random variables that are bounded. That's great. And now we have their sum. It looks like Höfding inequality now. Okay. Bounded means since they're bounded, they are sub-Gaussian. Any bounded random variable is sub-Gaussian. So it's less than, I'll just hide the constant here. And so this Höfding's inequality tells us that the sum is also sub-Gaussian. The sum of sub-Gaussian random variables is sub-Gaussian. And specifically, this is what we showed in this is a sub-Gaussian Höfding. From lecture 14 on October 3. If you forget this is okay. It's what really we are saying is that the increments of this process we can write as the sum of independent, identically distributed mean zero random variables that are sub-Gaussian. Okay, so then we have some concentration inequality. And even if you forget it, you look it up, and of course the sum will, by Höfding's inequality, be sub-Gaussian. Perfect. Okay, that's it. So now we just look at this, substitute each term, and it will be less than root n times f minus g. Each term is bounded like that, so have n of them. Sup norm. Yay! So that's good. So we proved that this process is sub-Gaussian, has sub-Gaussian increments that are bounded like this. Actually, sorry, it should be. Okay, so this sum is less than that. Then we divide by n here. So root n over n gives us 1 over root n. Okay. So this is true for any f and g in the class. Hey guys, are you with me? You're okay? Or was it a little too technical? I don't know.
I have a question.
Yes, go ahead.
So where we bounded Zi, there was we get rid of expectation.
Oh, Denise, sorry. Can you repeat from the beginning? I didn't catch the beginning of this phrase.
So Zi we bounded. I believe it should be a triangle inequality, or we assume that f minus g is positive.
Ah, yes. Yeah. Yeah, so
Some constant, I guess.
You mean that we haven't included this?
Yes.
Yeah, I didn't do that. Let's see. So we know that, okay, so we know that f minus g of xi is, this one is between -1 and 1, always. Sorry, what did we use? Okay, let me do it this way. Yeah, I should have been more careful here. So we know this for sure. So we know a bound on this thing. Then I'm claiming that if I have any random variable that stays, let's say, between -10 and 10, and I subtract its expectation, the result always is between -10 and 10. So if a random variable takes values between like -10 and 10, then that random variable minus its expectation also will take these values between -10 and 10. I think that's true. And then I don't have to consider this in expectation, and that's how I just can forget it. But if, to be more careful, because we don't really need that much precision, maybe I should have done the triangle inequality, and I would pay twice. I will pay factor 2, one factor to bound this and the other factor to bound that. But I didn't do this. Yeah. Did I answer your question, Dennis?
Yes, thanks.
Sure. Okay. So we're going to apply Dudley inequality. Dudley inequality requires us to find the good covering number. We found the good covering number. It's right there. So we're good here. What else Dudley inequality requires? It requires us to have sub-Gaussian increments. So that's what we're checking, have checked now, that the increments are sub-Gaussian. Why? Because they're naturally expressed as a sum of independent, identically distributed mean zero random variables that are bounded. And so everything is so good, concentration inequalities apply. And so the sum is sub-Gaussian. That's what we did, literally. Okay. One line, we're done. Apply Dudley. Dudley inequality. So this expected value, I'll continue it from here. Less than or equal to. So it's C times L, which is this. So I put it in front. C times L. Times this integral of log f infinity epsilon d epsilon. Good. That was a crucial step. Now everything is now becoming simple because, first of all, the upper bound, let's look at what we have here. For any epsilon greater than 1, the covering number is 1, which means that if I take the log here, log of 1 is 0, and the integral vanishes, the integrand vanishes. So really, it's the integral up to 1. Agreed? That's because the rest is trivial. Inside the integral, we have, let me show it again. Inside the integral, we have e to the c over epsilon. Now it's log of e to the c over epsilon, d epsilon, like this. Perfect. What can be better? This integral converges. There is no singularity at 0, actually, right? Because it integrates out. So this is about 1 over root n. Done. So we proved this theorem. Any questions? Good. Let's look at the theorem that we have proved. This one is a non-trivial one. We look at a class of all Lipschitz functions, and we can integrate any function, any Lipschitz function from the same sample. The immediate consequence for machine learning of this now I believe you can put it in the context of supervised learning, as we always do for hypothesis classes, is that the theorem allows for Lipschitz regression. Which means that if you have data, and maybe like this, so the data between 0 and 1, and then if we fit the best L Lipschitz function to the data, maybe like this, to the data, then the generalization error is, from this theorem, scales like 1 over root n, which is the same as in linear regression. So here the data, the data is red points, the fitting function is f, blue, and the data is xi, yi. And the generalization error is just the error of the error of the fit, additional error coming from the finite sample. This is unlike linear regression. This is a non-parametric regression. We don't parameterize the class in any way; just fit the best Lipschitz function, and surprisingly generalize as well. The same quality of generalization as the linear regression would do, for example. Okay, you need to do it yourself and just transport this theorem into the supervised learning in the way that we always do. For example, like in the last homework. Any questions?
I'm curious about, we always consider functions from 0, 1. How would the theorem change if we a bit more arbitrary domain function from A to B?
From A to B. I don't know exactly off the top of my head what the scaling parameter will be, but it will be kind of, you will pay something. Yeah, you need to check. I can't remember. You'll probably have something like the distance between A and B will show up somehow in this result, but I don't remember how. The proof definitely generalizes, as you can see.
Okay.
Yeah, sure. This is a good question. And even a more interesting question is what is for high dimensions, right? This is all in one dimension, from 0 to 1 or from A to B. What will happen in high dimensions? Because our data usually is high dimensional. So now, instead of looking at Lipschitz functions from the interval 0, 1, let's look at Lipschitz functions from 0, 1 to the D, so from D-dimensional cube in this case, to R, where F is 1 Lipschitz, or L Lipschitz. Guys, let's do 1 Lipschitz. Fewer parameters. 1 Lipschitz here means that F of A minus F of B is less than L times some distance between A and B. And in this case, the sup norm, the L infinity distance is natural. So this is what Lipschitz means, literally, here. Okay, things will become interesting now. It's not just a simple generalization. If we redo this lemma, so now we'll just go and just try to imitate the same proof. We need the covering number on this class. How did we find the covering number? We put the grid and approximated Lipschitz function of the grid. We can do the same in high dimensions, no problem. So instead of 1 dimension here, we'll have D minus 1 or D dimensions there. That's fine. And if you redo this properly, and I did it, you will get a similar statement. So it will be obviously 1 if epsilon is greater than 1. It's trivial regime, just one function approximates everything. And in the non-trivial regime, we had e to the c over epsilon. Now we will have e to the c over epsilon to the d. This is where the dimension will come. I'll skip this. This is the same proof essentially from the grid. Now we insert this into Dudley, just like before. And the Dudley integral, if you compute the Dudley integral, instead of this integral, like we had before, c, remember this? C over epsilon, right there. Instead of root of c over epsilon, we now have c over epsilon to the power d, to the power of d, like this. And that's bad news, because that diverges now. right? For even for d equal 2, we'll have c over epsilon. That's a function that's not integrable. Now suddenly we have a problem. This whole thing doesn't generalize to higher dimensions because Dudley becomes non-integrable. Yeah, you see the problem? Okay. There are two ways to go around this. One is to just say, okay, Dudley is too bad. Stop, and just abandon this whole idea. The other approach is to dig a little deeper. What goes wrong here? Something goes wrong around 0. So it is for small epsilon that we have a problem. Let's remember the idea, the proof of Dudley. And what happens for small epsilon? The whole proof of Dudley is chaining. This is a proof by picture. We establish a chain between t, the point where we want to be, and t0, the reference point, by walking in steps. First to t1, and t1 is in the epsilon net, and then we make a finer epsilon net, and then so the radius, the approximation increases and increases, t3, and then there is t4, and so on and so forth. And then eventually we converge on t. In this scheme, in this chaining, epsilons become smaller and smaller. So we get a better and better approximation, we get closer and closer to t. And that is where the problem is. The problem is that this integral is not integrable, it's a small epsilon. So something happens as we approach t, something bad happens. To fix that from happening, here's the idea, very, very simple idea. Just don't go all the way down to t, just stop short of t, stop earlier. So here's the fix, stop the chaining earlier. Namely, as soon as we get inside the neighborhood of delta neighborhood of t. Okay, so if we are already delta close to t, don't attempt to come closer because that will make the integral diverge eventually. Just stop at the delta distance if you can. The first point at the delta distance. And then the proof of Dudley will give us the following. T minus x t0 is less than, and here you have to just, I guess, believe me, that if we stopped short of like delta, we'll not go all the way down to 0. So we'll stop at delta. And what we pay is, well, now we have no control of what happens inside delta. So it's a worst possible situation where t and s are in t and the distance between them is at most delta. But we have the same, well, we're back to the same problem of bounding this process, but now in this ball of delta locally. So you need to check this, but this is really what chaining gives you. The main advantage of this is to not go down to 0 because that will cause the divergence. What we pay for this is that we can't control anything. Previously, this was 0, but now we can't control anything that happens in this delta. All right. Okay, believable, guys? Yeah, if you do, just do the proof and you'll see that exactly what happens if you stop early. Okay, let's do it. Let's apply this. Now, let's again redo the proof for high dimensions. So apply this for our xf is this, obviously, just like before. Okay, here we go. So we'll get expected value of xf just like before, is less than. This was our problem. So I'm rewriting the previous attempt now. This was a failed attempt. This is what we did before. Now let's fix this. So instead of going all the way to 0, we stop at delta. We pay, and we pay this. F and G are in F, and the distance, which is a sup norm, is less than delta. So we paid this term. So that's our fix. Okay, let's see how much we pay. Is it okay or not? So this is what? This is 1 over n sum f minus g of xi minus expected value f minus g of xi. Good. So f minus g. F minus g is always bounded by delta. So this is always smaller than delta. And we subtract something. So all in all, well, this is also smaller than delta in absolute value. So this is less than 2 delta. And that's it. We just pay 2 delta. Aha. Cool. So the first integral now converges. The first integral is now, let's see, it's 1 over root n. Then let me put c to the d up front, d over 2. And then 1 over epsilon to the d over 2. That's going to be something like d to the minus delta to the minus d over 2 plus 1, I think. I just integrate this, the polynomial e to the minus d over 2. Yeah, that's d plus 1, yeah. And then divided by d over 2 minus 1, but that's, skip that. That's in higher dimensions, even helping us. Plus 2 delta. Or plus delta, I'll skip the constant here. Okay, it's a mess, but now delta is in our hands. So now let's optimize. We can optimize delta. And I did this. It's a very simple exercise. So I'll not repeat it, you just differentiate this one. And the optimal choice, with the optimal choice, we get 1 over n to the power 1 over d. Okay, so all of this hard work gives us now the theorem in high dimensions. And it looks like this. We can integrate any Lipschitz function. And in particular, we can make Lipschitz regression happen. And the error is C. We did it for L equal 1, but it will be L here generally. N to the power 1 over D. That is our, for any dimension D, let's say greater than 2. So that's a result of this fix. And the fix is to stop chaining early. Good. Any questions about this proof before we interpret the result? So. Okay, so same idea, chaining, but just a little modification. Good. So in particular, Lipschitz regression works in higher dimensions. This is good news. Now there is one bad news. Why would not then do Lipschitz regression all the time? Well, here's bad news. To make this error small, we need to make this term large. This is the only term that drives down the error. How large is this term? This is e to the power log n divided by d. So let me write it this way. E to log n divided by d. So if we want this to be large, let's say even larger than 10, for example, that we will need log n to exceed d. So log n needs to be larger than d, which means that n has to be larger than x exponential of d, e to the d. Unfortunately. So what this means is that, unfortunately, to make the error small, one needs an exponentially large sample in dimension. And that means that Lipschitz regression suffers from the curse of high dimensionality. So one needs something else to lift the curse of high dimensionality, but we'll not go over there. In lower dimension, it works very nicely with dimension 1 and 2. Good. This ends our story about chaining and Dudley inequality. And next time, in our last time, we'll change gears completely, and I'll show you an example of a beautiful area that we haven't touched, concentration of measure, where you would where you can learn how to prove concentration inequalities for not sums of independent random variables, but any nonlinear function, any Lipschitz function, for example, of independent random variables. This area is out of reach for classical probability, which studies sums of independent random variables, which are linear statistics. But we'll learn how to work with nonlinear statistics in the same way. Any questions?
I have. So what happens when d is equal to 2?
What happens if
D equals to 2 without
yeah, that's a good question. If d let's check. Let's check what happens. So if d here, so I'm looking at here. If d equals to 2, then we have c over epsilon. Then instead of this term, let's rewrite it. We'll not need it anymore. So we'll have, so now d cancels this square root. So we'll have something like log of 1 over delta, I believe. Just like this. Plus 2 delta. Yeah. Then if you optimize this, it will give you something like, I think it will give you log n over root n with the optimal choice. So you will have here, you'll have log L, Lipschitz constant, log n over n. Yeah. Log n over root n, sorry. Over root n. So we will, this is dimension 2. So in this case, we almost recover the classical rate, which is root n up to log factor. And then you can ask if log factor is necessary. Here, can you do something a little bit better to remove the log n factor? Before I go into that direction, is it okay now? Yeah? Does that answer your question?
Yes.
Yeah. Okay. Sure. Now, if you want to go now you ask yourself, can you remove this log n? Okay, this is just I guess for aesthetic reasons or for the reasons of understanding deeply, not for practical reasons, but can you remove log n from here? Is it for a reason? You go to the proof and you discover that the log n here the log n is an indication that Dudley's integral, the whole, where is it? That this bound is not an optimal bound. So if you want to bound any stochastic process, Dudley is a very good tool. It's a practical tool. It's not difficult to apply like we did it today here, but it doesn't give you the best results. And sometimes it is just log factor off from the truth. So then you can ask yourself, well, what is the truth? What is the geometric quantity associated with a metric space that controls stochastic processes completely? That question was very important. It was open for many years, 20, 30 years, and was finally solved by Talleyrand. By Talleyrand in 1987. The keyword is generic chaining. If you want generic chaining or majorizing measures. Those are the keywords related to the solution of Talleyrand. The functional that controls T is called gamma functional, gamma 2 functional. I'll not explain what it is, but there is, the point is that there is a kind of a closed form, but there is a formula formula that only depends on the geometry of T, metric geometry of T, that controls the stochastic processes completely, which means that it is greater than gamma T for some processes and less than like gamma T, C gamma T, something like that. If you use that, the gamma T functional, it's much, much harder to work with than Dudley. So that's why I'm not recommending it to you. But if you do that and work very hard, then as one of the results, you can, in fact, get rid of the log factor. So it actually is not necessary. I can't remember who first proved it, but you can look at the work of Talleyrand, who put it in the context of majorizing measures and generic chaining. In this theorem, the keyword is matching theorem. So log factor is not necessary for dimension 2. Yeah. Any questions? You guys, did any of you study Wasserstein distance, maybe? No? Wasserstein distance, Monch-Kantorovich, optimal transport, no? Okay, no, not did, okay. Yeah, if you're here, it's not a part of the course.
Can you repeat this? Which distance?
Evgeny, sorry, you're cutting off. Can you repeat?
Yeah, can you repeat this once again? Which distance?
Wasserstein. Wasserstein.
Is it like number of different components, or is it?
No, it's an optimal
okay.
transport. It's an optimal transport distance. So this is like you have. So suppose you have points. Suppose you have points like this, let's say, and you have points like this. The same number of points, let's say. The question is to match, like to marry black points to red points, so that the total distance is smallest. So imagine you want to go from black points to red points, like to transport them, and you want to make this in this. You pay for the distance transported. So this was probably not a perfect thing to do. But the Wasserstein distance is the minimum, the minimal distance, total distance that you transport black points to red points. You're allowed to match them in any way you like. Okay, is it clear? Yeah. Okay. It's called optimal transportation problem. Optimal transport. More generally, you can you may ask about transporting a probability density, the black probability density, to the red probability density, different shape. And you pay for each particle that you transport, the distance of each particle transported. So what is the optimal way to do this? So that's Wasserstein distance between measures mu and nu, W2, mu and nu. Okay, why did I bring it up? Kantorovich-Rubinstein theorem expresses this transportation distance as what we've seen, it's supremum over all Lipschitz functions between the expected value of f of x minus expected value of f of x, where the expectation is with respect to these measures. So for the black points versus blue points, it will be like this, f of xi, I guess, minus f of yi. That's for the uniform distributions on the black point and uniform distribution on the red points. And f is a class of Lipschitz function, one Lipschitz functions. This is kind of a duality theorem. It says that the distance that the quantity that we've been studying in this couple classes, this one, or similar to that, this quantity, is very much related to the transportation distance. And in fact, it is equivalent to the question of transporting the sample to the original distribution, or vice versa, the sample to the population, or a sample to an independent sample. You just take two independent samples. And then it becomes a very cool problem. On the square, you take two independent samples, let's say from uniform distribution. Just like this. I took two independent samples, and the question is, how do we marry them? I want to transport them in, what's the Wasserstein distance? They want to transport black to red in the best way. And that's what we did, actually. If we knew that duality theorem, so we proved that the transported distance on average is what is it? It's 1 over n to the power 1 over d. So for example, in dimension 2, it was up to log factor, but we know, I said that log factor can be removed, so it will be like this. It's clear now that it is optimal. Because the distance, if you think about, if you put n points on the square, on the unit square, what's the average distance between them? It's going to be will it be 1 over root n? It's a little exercise, but you can check. If you just drop n points on the square, and what is the spacing? What's the distance between the neighbors? It will be 1 over root n. And so you can't really marry points better than that, right? Because you have to transport 1 over n. And generally, in dimension n, the average distance between the points will be this. If you drop n points on the cube of dimension d, that will be the average distance between them. And that means that you can't transport points better than that, but you can transport points like this. So you take two samples, and this theorem that we proved allows us to transport points in the optimal way. If we know a little bit about this duality, which I showed you. That's a reason why this theorem is called the matching theorem, because you match points between themselves. Good. Okay, I should probably stop talking now. So what? Any other questions? Okay, guys, very nice. Is there anybody else who wants to meet with me, or anybody, especially if we haven't met before?
We haven't yet.
Oh, Denise, we didn't meet with you. Okay, let's do that. Sounds good. Okay. Stop recording.